Physics Part 390, where n is the initial number of undecayed nuclei in the sample and n is the number of undecayed nuclei at the time t. This equation is exactly the same form as the one used to describe the decay of the current in a circuit containing a capacitor and a resistor. Note that the decay constant is analogous to the reciprocal time constant, that is 1 over CR. The equation represents exponential decay. The decay curve of n against t is as shown in the figure. Since activity A is proportional to n, the curve of A against t is the same shape, and we can write the equation accordingly. We've got another example for you. A sample of phosphorus 32 contains 8.6 into 10 power raised to 12 nuclei at a time t is equal to 0. The decay constant of phosphorus 32 is 4.8 into 10 power raised to minus 2 days, minus 2 per day. Calculate the number of undecayed phosphorus 32 nuclei in the sample after 10 days. From n is equal to n naught e, we have n is equal to 8.6 into 10 power raised to 12 into e. So it goes on. Now it's your turn. A sample of phosphorus 32 contains 8.6 into 10 power raised to 12 nuclei at a time. T is equal to 0. The decay constant of phosphorus 32 is 4.8 into 10 power raised to minus 2 per day. Calculate the number of undecayed phosphorus 32 nuclei in the sample after E, 20 days, and the sample after 30 days, B. Decay constant and half-life. Using equation n is equal to n0 e decay constant t, we can derive an equation which relates the half-life to decay constant. For any radioactive nuclide, the number of undecayed nuclei after one half-life is, by the definition of half-life, equal to n0 over 2, where n0 is the original number of the undecayed nuclei. Using the radioactivity decay equation, we form it and we take the logarithms and we equal the equation and find the resultant value. We've got another example for you. Calculate the half-life of radium-226, which has a decay constant of 1.42 into 10 power raised to minus 11 per second. Now it's your turn. Calculate the half-lives of the following radioactive nuclides. Bismuth-213, which has a decay constant of 4.3 into 10 power raised to 3 per second. Calculate the radioactive nuclides of carbon-14, which has a decay constant of 4.1 into 10 power raised to minus 12 per second. Number 2. Calculate the decay constant of the following radioactive nuclides. A. Helium-5, which has a half-life of 6.0 into 10 power raised to minus 20 per second. B. Sodium-24, which has a half-life of 15 H. We've got a section summary. The half-lives of T into half of a radioactive nuclide is the time taken for the number of undecayed nuclei to be reduced to half original number. Number 2, the activity of the radioactive source is the number of decays per unit time. The unit of activity is becquerel. 1 becquerel is 1 decay per second. The activity of dN over dt of a source is related to the number of n of undecayed nuclei by the equation. dN over dt is equal to decay factor n, where decay factor is in fact a constant. The decay constant is defined as the probability of the decay per unit time of a nucleus. The number of n of undecayed nuclei radioactive sample at time t is given by the equation, where n naught is the number of undecayed nuclei at time t is equal to 0. The half-life t into half the decay constant are related to the equation and simplified accordingly.